In today's video, we are going to learn how to determine the eigenvalues and eigenvectors of a 2 by 2 matrix. Now let's assume that A is a square matrix and then A times a non-zero vector x is equal to a scalar, which is lambda, times the non-zero vector. Now let's call this equation 1. So we have A to be a square matrix, or better still, an n by n matrix. X is said to be the eigenvector of A corresponding to lambda, and then lambda is the eigenvalue of A corresponding to x. Now in a typical problem, it is usually desired to find the eigenvalues as well as the eigenvectors that satisfies equation 1. And since x equals 0 is always a solution for any value of lambda, we are usually not interested in that. Now our interest is to admit solutions with x not equal to 0. So that is what we are interested in, to admit solutions with x not equal to 0. Notice that the matrix A in this case can have multiple eigenvalues, that is multiple values of lambda, but the number of values of lambda cannot exceed the number of rows or columns of matrix A. Also remember that each eigenvalue corresponds to a specific eigenvector. Now to determine the eigenvalue as well as the eigenvectors of a given matrix, let's consider equation 1. So from equation 1 we have AX equals lambda x, and then what we are going to do is we are going to insert the identity element in between lambda and then x on the right hand side of the equation. So we are going to have AX equals lambda IX. Now let's call this equation 2. Notice that this equation is not a new equation, or is not so different from equation 1. You can basically consider that as multiplying any value by 1. Now realize that when you multiply any value by 1, it is nothing but the value itself. So we say that the identity element here is nothing but the matrix equivalent of multiplying by 1. Now let's transpose whatever we have on the right hand side onto the left hand side, so that we have AX minus lambda IX equals 0, and then we factor out x since it's common to both terms. So we have A minus lambda I in the bracket times x equals 0. Let's call this equation 3. Now this system will have a solution if and only if the determinant of A minus lambda I all times x is equal to 0. Notice that this matrix, which is A minus lambda I, is a singular matrix because its determinant is equal to 0, and therefore this matrix has no inverse. Also, the determinant of this matrix, that is the determinant of A minus lambda I, gives rise to a polynomial, and we call this polynomial the characteristic polynomial. And the equation formed when the determinant of a minus lambda I equals 0 is called the characteristic equation, and the solutions to this equation are called the eigenvalues. So in the next section, we are going to take an example of a 2 by 2 matrix and then try to find its eigenvalues as well as the corresponding eigenvectors. So let's try that example. Find the eigenvalues and eigenvectors of A, and this matrix has entries 2, 1, 4, 5. So let's try to solve this example. First of all, we are going to find the eigenvalues. Now in the previous section, we said that the solution to the determinant of the matrix A minus lambda I equals 0 gives the eigenvalues. So this is the equation we are going to use to find the eigenvalues. So let's try to determine this matrix, that is the matrix A minus lambda I. So we have matrix A giving us 2, 1, 4, 5 minus lambda times the identity matrix, which is 1, 0, 0, 1. So basically this is the identity matrix for a 2 by 2 matrix. Now we are going to multiply lambda by each value of the identity matrix. So multiplying lambda across, we are going to have lambda 0, 0, lambda. So that's going to be lambda 0, 0, lambda. And let's try to evaluate this. So we have 2 minus lambda, 1, 4, 5 minus lambda, and that is the matrix A minus lambda I. Now let's try to find the determinant of this matrix. So the determinant of A minus lambda I is equal to, we have 2 minus lambda, 1, 4, 5 minus lambda, and that is equal to, we are basically going to multiply this value by this value. So that is 2 minus lambda times 5 minus lambda minus this value times this value. So 4 times 1. Now let's multiply these two. So 2 times 5 is 10. 2 times negative lambda is negative 2 lambda. Negative lambda times 5 is negative 5 lambda. And then negative lambda times negative lambda is plus lambda square. Now we have negative 2, negative 5. So let's just simplify this so that we have negative 7 lambda plus lambda square minus 4. And then 10 minus 4 is 6. So we are going to have lambda square minus 7 lambda plus 6, and that is equal to 0. Now the coefficient of lambda square is 1, coefficient of the constant is 6. So we need to find the factors of 6, that when you multiply you are going to get 6, and then when you add them up you are going to get negative 7. So we know that negative 1 times negative 6 is 6, and then negative 1 plus negative 6 is negative 7. So this becomes lambda square minus lambda minus 6 lambda plus 6. So we factor out lambda, and then we have lambda minus 1, and then minus 6 into bracket lambda minus 1 equals 0. So we have the factors to be lambda minus 1, lambda minus 6, and that is equal to 0. So we have lambda minus 1 equals 0, and then when you transpose negative 1 to the right hand side, you have lambda equals 1, and you do same for lambda minus 6, and then you have lambda equals 6. So these are called the eigenvalues of this matrix. So let the first value be lambda 1 and the second value be lambda 2. So we have lambda 1 to be equal to 1 and then lambda 2 to be equal to 6, and these are called the eigenvalues. The eigenvalues of A. Now at this point, we are going to find the eigenvectors that corresponds to lambda 1 and then lambda 2. So to find the eigenvectors that correspond to lambda 1 and lambda 2, let's take the eigenvalues one at a time. So we have when lambda, or better still, lambda 1 is equal to 1. We are trying to find the eigenvector that corresponds to this eigenvalue. Now from equation 3, you remember that in the previous section we had equation 3 to be a minus lambda I all times x equals 0. This was equation 3 for the previous section. Now this is what we are going to use to find the eigenvector that corresponds to this eigenvalue. Now let's go back to our solution for the eigenvalues. You realize that we had a minus lambda I to be 2 negative lambda 1 4 5 negative lambda. So a minus lambda I is equal to the matrix 2 minus lambda 1 4 5 minus lambda. Now from equation 3, we are going to have this matrix 2 minus, now we have lambda 1 to be 1, so that's going to be 2 minus 1, and that is 1 1 4, and then 5 minus 1 is 4. So we have the matrix 1 1 4 4 times the non-zero vector x1 x2 equals the zero vector 0 0. Now at this point, we are going to transform this system of equations into an augmented matrix. So we are going to have 1 1 0 4 4 0. Now let's try to perform elementary row operations on this matrix to convert this augmented matrix to the row echelon form. So by this, we are going to make sure that this value goes to 0. Now what you are going to do is we are going to perform the operation on row 2, and the operation is we are going to multiply row 1 by 4 and subtract that from row 2. So we have row 2 minus 4 times row 1, and that's going to be elements in row 1 remains the same, and then for row 2 we have 4 times 1, so 4 times 1 is 4, 4 minus 4 is 0, and the same applies to this, 0 minus 4 times 0, and that is also 0. So we have this to be the row echelon form of the augmented matrix. Now we have this to be x1 and then this to be x2. So we say that we have x1 plus x2 equals 0. Now let's transpose x2 to the right hand side so that we have x1 equals negative x2. Now at this point, let's choose any arbitrary value for x2. So let x2 be equal to 1. Now if x2 is equal to 1, then we have x1 equals negative of x2, so negative 1, and thus the eigenvector x, which has elements x1 negative 1 and then x2, 1, is the eigenvector of A corresponding to lambda 1 equals 1. So at this point, we've been able to determine the eigenvector of A that corresponds to lambda 1 equals 1. Now let's find the eigenvector of A that corresponds to the eigenvalue lambda 2 equals 6. So for lambda 2 equals 6, starting from this point, we have A minus lambda I equals 2 minus lambda 1, 4, 5 minus lambda, and that is equal to, since lambda 2 or lambda here is equal to 6, then we have 2 minus 6, that is negative 4, 1, 4, 5 minus 6 is negative 1. So we have negative 4, 1, 4, negative 1 times the eigenvector x1, x2 equals the 0 vector which has elements 0, 0. So at this point, we convert this system of equations to an augmented matrix. So we have negative 4, 1, 0, 4, negative 1, 0. Now let's try to perform elementary row operations on this augmented matrix to convert that to the row echelon form. So at this point, we are going to perform the operation on row 2, because the idea is to make this value go to 0. And so in doing that, we are going to have the operation to be R1 plus R2. Now if you should add negative 4 to 4, you are going to get this value to be 0. So that is why we have this operation here. So elements in row 1 remains the same, and then we apply changes to elements in row 2. So we have negative 4 plus 4, that is 0, and then 1 plus negative 1 is also 0. 0 plus 0 is also 0. Now we can choose to divide equation 1, or better still, multiply equation 1 by negative 1 over 4. So we have negative 1 over 4 times R1, and then this becomes negative 1 over 4 times negative 4. 4 cancels out 4, we are left with 1, and then negative 1 times negative 1 becomes 1. 1 times negative 1 over 4 is negative 1 over 4. 0 times negative 1 over 4 is still 0. And then for row 2, we have 0, 0, 0. So this is the row echelon form of the augmented matrix. Since we have this to be x1, x2, then what this primarily means is that we are going to have x1 minus 1 over 4 x2 equals 0. At this point, we are going to transpose negative 1 over 4 x2 to the right hand side, so that we have x1 equals 1 over 4 x2, and then we choose any arbitrary value for x2. So let x2 equals 1. So if x2 equals 1, then we have x1 to be equal to 1 over 4 times 1, which is equal to 1 over 4. Therefore, we say that the eigenvector which has components x1 1 over 4 and then x2 1 is the eigenvector of A that corresponds to lambda 2 equals 6. So in summary, we have the eigenvector -1, 1, corresponding to the eigenvalue lambda 1 equals 1, and then the eigenvector 1/4, 1, also corresponding to the eigenvalue lambda 2 equals 6.